Okay, welcome back to linear algebra. Continuing our work in section 5.2. V remains a finite dimensional vector space, talking about operators on V called T. If we take an eigenvalue lambda for this operator T, then by E sub lambda, I mean the null space of the operator T minus lambda IV. That is the set of vectors in V that are eigenvectors with that eigenvalue. Okay, so we're going to denote that by E sub lambda. It's a null space, so it's a subspace. We're going to call it the eigenspace of T corresponding to lambda. Okay, so every eigenvalue comes with its eigenspace, the space of eigenvectors that have that eigenvalue. As usual, if you're starting with a matrix, if I talk about the eigenspace of a matrix, I mean the eigenspace of the linear operator that's left multiplication by that matrix. All right. First theorem of the lecture, 5.7, is the following, that if you take an operator T from V to V, take an eigenvalue of it, and it has, say, multiplicity m greater than 0, so that T minus lambda to the m occurs in the characteristic polynomial, then the dimension of this eigenspace, well, it's at least 1, but it's no more than m. So the essence of this theorem is that the multiplicity of the eigenvalue lambda in the characteristic polynomial is a cap on the dimension of this eigenspace. The eigenspace can't be any bigger than that. I'll say this at the end of the proof, but of course the eigenspace has dimension at least 1 because eigenspaces are not empty. Or excuse me, they're not 0, I mean, right? Because eigenvectors are not 0. So if lambda is an eigenvalue for T, it's got to have a non-zero eigenvector in it. So E sub lambda is never 0. So that's why the dimension's at least 1. It's never a 0-dimensional space. Okay, so how to prove this? How to prove the multiplicity caps the dimension of the eigenspace? Well, pick a basis for this eigenspace. So we're saying its dimension is k in this notation, and then extend that to a basis for the whole space. So you've got the first k vectors are a basis for e lambda, and then you add as many more as you need. I'm going to say the dimension of v is n. We can always extend that to a basis for all of v. Okay, well, in that beta basis, T won't be diagonal, but it's got kind of a k by k block that is diagonal because for the first k vectors in that basis, T of them is lambda times them. So the matrix for T in that basis would have this k by k block that's diagonal with diagonal entries lambda, and then it would have zeros below that because we're not because again, for any vector v1 to vk, T of it is lambda times it, and then there's some other components in this matrix. I'm just calling them B and C. Okay, shorthand, let's just call that matrix A. So the characteristic polynomial, ft, it's the determinant of A minus t times the n by n identity matrix. And by a property from the determinant section, this matrix, if you take the determinant of that matrix, A minus t times in, well, you're going to get you're going to get lambda minus t times itself, k times, I wrote t minus lambda, so that's why I've got a minus 1 to the k out front, times the determinant of that lower corner, c, minus t times I, the appropriate size identity matrix. Well, this little block down here would be n minus k by n minus k. Okay, so that's the characteristic polynomial. So the multiplicity m of lambda is at least k, because look, I've got at least k factors of t minus lambda in the polynomial. Maybe there's more. Maybe there's some other factors of t minus lambda in this part, but there's at least k factors there. Okay. And like I said above, the dimension of E sub lambda is at least 1, because if lambda is an eigenvalue, then it's got a non-zero eigenvector. So this dimension, E sub lambda, it's no more than m, but it's at least 1, and that's what the theorem says. Nice. Let's look at an example. Taking a 3 by 3 matrix A here. Let's try to find all of its eigenvalues, and let's find bases for its eigenspaces. Okay, so I'm basically asking the question, is A diagonalizable? Can we find a basis of eigenvectors? I'm going to do this with a Mathematica. So maybe I should leave that visible there, but here I am inputting Mathematica, the matrix A. So to display it, I can use that matrix form command. So there's the matrix A. Looks like I inputted it correctly. Finding the characteristic polynomial, well, you take the determinant of A minus T times the appropriate identity matrix. So I'm leaving T in there as a variable. That's what this underscore over here does, if you're wondering. It's just, it says, that the T is not a fixed thing that I'm defining, but rather a variable that can take on different values. So it displays the characteristic polynomial. There it is, and Mathematica can factor it for me. So the factored characteristic polynomial looks like that. I'm going to just rewrite it in notation that looks a little bit more familiar, writing it negative t minus 1 times t minus 2 quantity squared. Okay, so we have two eigenvalues, and they are lambda is 1 and lambda is 2. Their multiplicities are 1 and 2, respectively. Okay, so to find some eigenspaces, let's pick the smaller one first, lambda 1, I'll call it, is equal to 1. So I look at A minus 1 times the 3 by 3 identity matrix. I'm having Mathematica row reduce it for me. Putting it in matrix form, it looks like that. So I can see from that matrix, maybe I should write this closer to it, but I'll write it over here. That matrix is telling me that something is in the null space if and only if x1 plus 2x3 is 0. And x2 minus x3 is 0. x3 is a free variable. It's an element of, well, I wrote R, the field in general. Yeah. So I've got one free variable. If I pick its value to be 1, then those equations dictate that x2 will also be 1 and that x1 will be negative 2. So there's a basis for the eigenspace E sub lambda 1. It's one-dimensional. Okay, we knew it was going to be one-dimensional because the theorem says that that's a cap on the dimension of that eigenspace. The eigenspace is at least one-dimensional and no more than one-dimensional, so okay. But for the eigenvalue lambda equals 2, there's a couple of possibilities. I know that its dimension is no more than 2, but it could be 1. So let's check it out. We'll let Mathematica do the heavy lifting for us here. So we're taking the eigenvalue lambda is equal to 2. So I'm looking at A minus 2 times 3 by 3 identity matrix, row reducing it, putting it in matrix form. You can see it there. So what does that thing tell us? That tells us that something would be in the x1, x2, x3 is in the null space if and only if x1 plus x3 is 0. X2 is free. There's no condition on it at all, and x3 is free. So we actually have two free variables. So if I choose x3 to be 1 and then choosing x2 to be 0, then I would get the vector 1, 0, negative 1. And if I choose x3 to be 0 and x2 to be 1, I get kind of the standard basis vector 0, 1, 0. So the dimension of that eigenspace actually ends up being 2. Okay. We know from previous work that eigenvectors from different eigenspaces are independent. So if we roll that together, we get a basis of eigenvectors. Okay, take one eigenvector from E lambda 1, the other two eigenvectors from E lambda 2. There's 3 of those things. They're linearly independent, so we've got a basis. We've got a basis. So our operator, our matrix rather, A is diagonalizable, and the linear operator L sub A in this eigenvector basis would be the diagonal matrix 1, 2, 2. Cool. If you want to conjugate to get that matrix, right? What would be the change of basis matrix? You just take Q to be, you put the eigenvectors in the columns. Okay, and then you can check that Q inverse times A times Q is equal to the matrix that's written above there, that diagonal matrix. Nice. Okay, continuing our theory here a little bit, we're going to prove a little bit of a lemma for the next theorem. So it's about an operator on a finite dimensional vector space. You got k distinct eigenvector values, so no two of those are equal. And then for each index between 1 and k, pick an eigenvector corresponding to the eigenvalue lambda I. And then the lemma says that if you add those eigenvectors together and get 0, they all must have been equal to 0. Okay. So how are we going to prove that? Well, if they're not all 0, then we can kind of renumber them if we want, reorder them. Let's suppose that the first m of them aren't 0 and the last m of them are. Okay, that would be true for some m between 0 and k if they're not all 0. So you can just drop off the ones that are 0, and we would have that v1 up to vm added together is 0, and none of those things are 0. But we proved those are eigenvectors with different eigenvalues. We proved in Theorem 5.5 that that set is linearly independent. Okay, so that's a contradiction. You cannot add a bunch of linearly independent vectors together with coefficients equal to 1 and get 0. So where did the contradiction come from? The contradiction came from supposing that that not all of those VIs were 0, so they must be 0 for all I. Cool. So we're going to use that lemma to prove Theorem 5.8. Theorem 5.8 says if you take an operator on a finite dimensional vector space, it has k distinct eigenvalues. Okay. So now for each index I between 1 and k, if we choose a subset Si of the corresponding eigenspace, and we choose it so that it's finite and linearly independent, then the theorem says if you union all those subsets together, you still have an independent set. Okay, so if you union together finite independent sets from distinct eigenspaces, the union is independent. Okay, how to prove this? Just set up some notation. So for every index between 1 and k, let's suppose that we call the finite linearly independent set Si, let's call its elements vi1, vi2, and so on up to vi, and then I wrote n sub I because these sets aren't necessarily the same size. Okay, so n sub 1 is the size of S1, n sub 2 is the size of S2. They're not all necessarily the same, but that set is a subset of the corresponding eigenspace. Okay, so in that notation, if we union all those things together, what would we get? Well, we get a bunch of things that look like Vij. I is a number between 1 and k, and then j goes between 1 and, well, whatever n sub I is. So I'm trying to show that S is linearly independent. So suppose I take a bunch of scalars, I'm going to call them Aij, and I multiply those scalars by these Vij's, and I add them all together and get 0. Okay, so I'm summing over the j's from 1 to ni, and then summing over the i's from 1 to k. That's just summing over all these sets. Okay, so let's denote by W. I'm putting some brackets around it. Let's let Wi, rather not W, Wi is the Aij's times Vij's for a fixed I. Okay, so I have a W1, a W2, and so on. Those W's are in the ith eigenspace. That's because Vij for a fixed I all come from E sub lambda I, and E sub lambda I is a subspace. Some scalar multiples of vectors from a subspace, you stay in the subspace. Okay, and then this equation is just saying that the sum as I goes from 1 to k of W sub I is equal to 0. So that's what I'm writing down here. That sum is equal to 0. Well, the lemma says that all the Wi's are 0. Okay, because those things come from distinct eigenspaces, W1, W2, and so on. So if they sum up to 0, they're all equal to 0. But if all those W's are equal to 0, so the W's are the things in the red brackets. So if you think about just like W1, well, W1 is a linear combination of things from this S sub 1, but S sub 1 was a linearly independent set. So all the coefficients would be 0. And that's true not just for I equals 1, it's true for all values of I. So all those coefficients are 0 for all values of I and j. Pardon me, I should write for all I and j. Oh, I did write it. I'm not looking at my own notes, pardon me. So it's for all I between 1 and k and all j between 1 and n sub I. And the reason that's true is because S sub I is linearly independent. Okay, so that proves that theorem. As a corollary to it, if you take a basis for each eigenspace, if beta I is a basis for E lambda I for all I, then the union of the betas is linearly independent. I'd like to say that it's a basis for V, but it might not span. There might not be enough of them. But if you take bases for each eigenspace and lump them all together with the union, you at least get a linearly independent set. If it has the right number of vectors in it, it's a basis for the space, and so your T would be diagonalizable. But in general, it might not have enough vectors in it. Okay, this is the last theorem for this lecture. It's kind of a complicated theorem to state, but it's not that bad to prove. So let me try to walk you through what it's saying. Take an operator on V, finite dimensional. Suppose its characteristic polynomial splits. Okay, factors into linear factors. Let's call the distinct eigenvalues lambda 1 to lambda k. Okay, so no two of those things are equal. Let's let mi be the multiplicity of the ith eigenvalue for every k. So that's the exponent on t minus lambda I in the characteristic polynomial. And remember, this characteristic polynomial completely splits. Okay. So there's two parts of the theorem. One part is that T is diagonalizable if and only if those eigenspaces have maximal dimension. We know from our earlier work in this lecture that the dimension of that eigenspace is no more than mi. So if it equals its maximum value for every I, then the operator is diagonalizable and vice versa. And then secondly, and we'll kind of prove this as we go, but we're stating it as a second part, that if T is diagonalizable and you pick the basis for each eigenspace, then the union of those things will be a basis for V. Okay, so we have already proven that the union is linearly independent. So if T is diagonalizable, there's sort of the right number of elements in that union. That's the gist of it. Okay. So let's try to prove this stuff one at a time. Part one's an if and only if proof. We said that we have a characteristic polynomial that splits. So let's write down the notation for that. So the characteristic polynomial is the product of t minus lambda 1 times t minus lambda 2 raised to the appropriate multiplicities. And because this thing is the characteristic polynomial, its degree is the dimension of V. Its degree is also the sum of those multiplicities. And so the sum of those multiplicities has to equal the dimension of V, which I'm calling N, like usual. Okay, so now the if and only if part. Let's suppose T is diagonalizable. Okay, so that means there's a basis of eigenvectors. Okay, so if I let, say, beta sub I be that basis intersect E sub lambda I for all I, and then let's say that beta sub I has ni elements, well, then ni is certainly less than or equal to the dimension of that ith eigenspace, right? Because it's beta sub I is a linearly independent subset of that ith eigenspace, and so you can't have more than the dimension vectors in there. Okay, so that's just because beta sub I is a subset of this and it's linearly independent. All right, well, moreover, we proved above that the dimension of that eigenspace is less than or equal to mi. That was the first theorem of this lecture. So if you stitch those two things together, it says that ni is less than or equal to mi for every single value of I. Okay, so that would mean n, which is certainly the sum of the ni's, right? Because beta is a basis. So the union of the beta i's, their disjoint, it's going to be the number of elements in the basis beta. That sum would be less than or equal to the sum of the dimensions, right? Because ni is less than or equal to the dimension for every I, but the dimensions are less than or equal to m, so that sum is less than or equal to the sum of the m's, but we wrote above that is equal to n because this polynomial splits. So the polynomial splits, the multiplicities of its zeros add up to its degree. Well, then that means since the n is the same on the left and right hand side of those inequalities, all those inequalities are actually equalities. Those numbers are actually all equal to each other. I'm just going to write that over that. So in particular, if I subtract the dimension of E at lambda I, the sum of them from the sum of the mi's, and do the algebra, I have to get 0. Because those two sums are equal to each other. Okay, but mi is greater than or equal to the dimension of E lambda I. So there's no negative numbers in that sum. They're all non-negative numbers. Well, if you add a bunch of non-negative numbers up and get zero, every one of the numbers was zero. So actually, mi has to be the dimension of e lambda I for all I. And that's what we were trying to prove. Nice. Going the other way, if we suppose that ei's dimension is mi for all I, and we let beta I be a basis for that eigenspace, well, then that basis has the dimension number of elements in it. Okay. So by theorem 5.8, well, really by its corollary, the union of those things is a linearly independent subset of V, and it's got the right number of elements. Beta would be the sum of these MIs, right? But that has to sum up to equal to n. So beta is a basis because it's a linearly independent subset with the right number of elements, and that means that T is diagonalizable. Cool. Okay, the second part of the theorem, we actually kind of already proved it. The last part of the argument that we just gave shows that if you take beta I as a basis for each one of the eigenspaces, then the union of them is a linearly independent subset of V, and the number of elements in that union would, of course, be the sum of the number of elements in each component because they're disjoints, right? Because these things come from distinct eigenspaces. Well, if T is diagonalizable, that sum of the beta i's has to add up to the dimension of V, right? Because we have to have a basis of eigenvectors. So therefore, beta is a basis for V. It has the right number of elements in it, and it's linearly independent. I'm just really kind of recapitulating. Okay, that's it for this lecture. Thanks for listening.